Welcome to the video lecture on simulation of solid-state drives using MATLAB Simulink. In this video, let us try to simulate the DC machine in a closed-loop operation by using converter-fed DC drive. So I have taken the same Simulink model which we have been looking into in the previous video. Let me remove this DC sources. Now this DC sources has to be fed from a converter, which is a full bridge converter. So for which I need a full bridge converter. So let me construct the full bridge converter first. So to construct a full bridge converter, let me try to open a new Simulink model. Let me try to, this is not this. Let me try to create a new Simulink model, blank model. In this model, we will create it, copy the thing, and we'll go paste it in this simulation file. So let me try to open the Simulink browser, library browser. In the library browser, I'm going to go to Simscape, electrical supply specialized power systems, power electronics. In power electronics, let me try to take the thyristor. Yes, thyristor, because I am going to have a controlled rectifier. Controlled rectifier output will be given to armature as well as the field. So I will take 4 thyristors. Let me rotate this thyristor, keep it comfortably on the screen. I'll have 4 thyristors like this. Okay. Now I'll connect this armature and cathode and anode, these 2 cathodes and these 2 anodes. Now, for these 2 thyristors, we have a common gate signals, and for these 2 thyristors, we have a common gate signal. So the gate signal is common to diagonally opposite thyristors, and this is supposed to be the positive and negative output of the control rectifier, and this is supposed to be the phase and neutral input of this control rectifier. So double click on this, and this measurement is not needed right now. So show measurement port, you can remove that. This also you can remove. All this 4, you can remove the show measurement port. We'll remove all this show measurement port. You pop on. Now select everything by pressing Ctrl A, right click, create subsystem from selection. This will create a model something like this. Double click inside, go inside. This is supposed to be your phase, and this is supposed to be your neutral input. Neutral. And this is supposed to be the positive output, and this is supposed to be the negative output. And this is supposed to be the gate pulses for thyristor T1 and T2, and this is supposed to be the gate pulse for thyristor T3 and T4. Now you come out, you could able to see this negative is supposed to come on the right side, just drag it. This neutral has to come on the left side, right? So this is supposed to be the control rectifier model. I copy this, I can cut this and put it on my this tray. Yes. Now this is the control rectifier. I have to give it to positive and negative of my armature. Positive and negative of my armature. I hope you could able to follow this. Positive and negative of my armature. Similarly, I copy the same one that has to be connected to the positive and negative of the field. So field is excited separately, armature is excited separately. And this is supposed to be your power supplying blocks to the machine. Okay. Now I need a input supply. Input supply, again you can go to Simulink library browser. The Simulink library browser, you can go to Simscape. In Simscape, you have specialized power systems. In that, you have a sources. In sources, you have a voltage source. So voltage source, I just drag it and put it on the screen. Phase motor, and the same one. You can just control and drag it here. Phase and neutral. So the same phase and neutral is given to both the input, both the converters. So double click on this AC voltage source, keep peak amplitude as 500, frequency as 50. Click apply and then give OK. Let me select everything, drag it a little bit on this side, have it comfortably on the screen. Okay. So this one, we need to generate firing pulses for T1 and T2, T3 and T4, T1 and T2 and T3 and T4 separately for this. This is actually armature converter. Armature converter. And this is actually a field converter. Field converter. So let me save this model as test2. Save it. Okay. Next part is we need to create the control signals for these two converters by using cosine firing angle scheme. The details of cosine firing angle scheme video is given in the description box below. You can make use of that to understand how a cosine firing angle scheme is working. So to create a cosine firing angle scheme in MATLAB Simulink, again I will go to the untitled version. I need to have 4 sine sources. So Simulink, go to Simulink sources. You take a sine wave. I need double click on this, keep this as 5 amplitude and frequency is 2 into pi into 50. Pi should be in small letters, that is why it is showing error. So this pi in small letters, click apply and give OK. So I need 4 such waves. I have taken 4 such waves and I need a relational operator which is available in commonly used. I take a relational operator and the first relational operator is supposed to be greater than and the second relational operator is supposed to be less than. Okay. So I connect like this, again greater than, connect like this, again less than, connect like this. Then I need a constant block. You can just change these constant blocks to 0. You can just go to the description box, look at the video related to cosine firing angle scheme implementation and the details of it theoretically. In the description link given below, I have given a video. You can just go there and understand it. Constant block. Okay, and this is also supposed to be the constant block, these two. Okay, then I need a converter because this is a different style. So I convert this, convert this, convert this, convert this. I put a conversion block and these two is supposed to be the control signal. So let me connect these two as a control signal. Now I need a logical operator and logic, one to this, another to this, and another one to this and to this. So this is supposed to be the control signals for T1 and T2 and this is supposed to be the control signals for T3 and T4. So here again sine wave 1, I should have a phase of pi by 2 in sine wave 1. In sine wave 2, I should have a phase of pi. In sine wave 4, I should have a phase of minus pi by 2. Minus pi by. So these are all some of the essentials that you have to do before creating it. So create the subsystem from this and reduce this. This is supposed to be your control signal. And this is supposed to be at thyristor T1 and T2. And this is supposed to be the signal for T3 and T4. So let me go back. Copy this, and put it on this screen as a control signal for these two. This one, and similarly, there should be a control signal. I just drag this down for it. It will be easy for me to connect. T3, T1, T2, T3. So control signals. Now the actual block diagram is something like this. I have to sense the current, compare with the reference current, give it to a PI controller, and that has to be given to the as a control signal. Similarly, I have to sense the speed, compare it with the reference speed, and this has to be given to a PI controller, which in turn generates the reference current. This is the complete system block diagram of a closed loop control of converter fed DC motor. So the same one we are going to implement in our simulation also. So for which I need a PI controller. So go to Simulink library browser. In Simulink, in continuous, you have a PID controller. Drag and put it on the screen. So this PID controller is there are two PID controllers required. One is for the current and the other one is for the speed. So there are two PID controls I have taken. Then I need a comparison block, actual with reference. This is actual and this is with reference. Similarly, this is actual current, this is reference current. This is reference current, this is actual current. So I need a sum block, for which again you can go to Simulink library browser. You have a sum block. This sum block is needed. Double click on this sum block. Change this plus to 1 plus 2 minus. So there is a plus and minus. So this is the actual speed and reference speed. The plus is supposed to be the reference and this minus is supposed to be the actual. And similarly, here also I need to have some actual and reference. Okay, so this is supposed to be the block. So I connect it like this. Now we need to set the parameters of this. This is actually a speed controller. And this is supposed to give the current control. So current control. Okay. The speed controller, double click on the speed controller. You need to use a PI controller. By default, it is PID. Choose a PI controller. Keep the proportional constant as 0.2. Integral constant as 5. Go to saturation tab. Give limit output. Provide upper limit as 20 because armature current maximum value is 20. And lower limit as 0. And in the anti-wind up loop, use clamping method. Click apply and do OK. Similarly, here the current controller, double click on the current controller, choose PI controller, keep proportional constant as 0.5 and integral constant as 30 and anti-winding loop, saturation. You go to saturation, limit output, give as 5 and 0 and clamping as anti-winding method. Click apply and do OK. Now this is supposed to be the actual speed and this is supposed to be the actual armature current. Actual speed is being sensed here. So you can just connect like this. This point is connected here, and this actual current is being sensed, and it has to be connected to the armature current, actual armature current, which is sensed. And I need a constant block for the field controller control voltage. I'm not going to change the field voltage, so I keep it constant, which is supposed to be 4.75. This is only armature control. I'm not making any field control. So let me give a speed of 1500 RPM here as a reference speed, and I should see that whether my motor is running at the same speed or not. So here I want to observe 1500. Now this is my reference speed. So before running the simulation, let me have some sort of uh, uh, configurations which has to be done in the Simulink diagnostics. Go to Simulink diagnostics, go to solver, keep the speed as stop time as 8, keep ODE 23 TBS solver. Solver details, you keep it as 1 e power small e power minus 5, minimum step size as 1 e power minus 6. Click apply and give OK. Then everything is set right now. Let me run the simulation and see whether my motor speed is running at 1500 RPM or not. Let me run the simulation. Cut this. Speed is slowly coming up, and now it is oscillating exactly around 1500. You could able to visualize the simulation pane. You could able to see that the simulation, it is around oscillating exactly around 1500. If you look at the graph, you'll get more clear picture on the results. Let the simulation complete. We'll wait for the simulation to complete and see how this speed is oscillating around 1500 RPM. This is how the simulation should be working actually. And now if you look at the simulation is going to complete now. Let us complete it and look at the speed now. Double click and look at the speed. The speed is around 160 radians per second. So let me have in the RPM also another scope on the RPM side. Let me run the simulation for 4 seconds minimum time. Run the simulation. Initially, the speed will be going down and coming up. This is the actual speed which is sensed by the motor. Let me run the simulation and waiting for the results. Let us see. Look at this. Yes, the speed is exactly at 1500. You can just zoom this part and see. It is exactly at 1500 oscillating, very nearer to 1500 RPM. So now what I can do is, I can again go to simulation, library browser. I can have a step change in the speed. Go to sources. You have a step source, a step source, and give this, change this to, remove that and change this to step. Double click on this step. Step time, let it be some 3. Initial value 1500. Final value 1700 or 1600. Initial value may be 1300. Initial value I can give it as 1300 and final value it will be 1700. 3. The time in which initially it is running at 1300 RPM. At 3 seconds it will go to 1700 RPM. We have to observe a similar change in this scope. That is what our objective is. Click apply and give OK, and I'm running for 6 seconds now. Run the simulation. Look at this. Initially it should be 1300 RPM. It should oscillate around 1300. Look at this. It is oscillating around 1300. Once the time is becoming 3 seconds, it has to go to 1700 RPM. Let us wait for the third second to come. Now it is 3 seconds. Now look at this. The speed has changed to 1700 RPM. So this is how the closed loop simulation should work, and our simulation is perfectly working like this. Uh, yes. Now look at this. Yes. Initially it is 1500, 300, and now it has jumped at third second. At third second it is jumping to 1700 RPM. So this is how we will run the simulation. Now let us go for change in the load torque condition. So for example, now the simulation is running. At 3 seconds, it will jump from 1300 to 1700. Meantime, what I will do, I will change this speed to 25 Newton meter and see whether the same speed is matching or not. Again, look at this, the speed is not changing. Speed is remaining constant. Now at third second, now it is jumping at 1700 RPM. Now the speed is, torque is 23. I reduce the torque to 20 again. Look at this. Again, the speed does not change, right? So this is again, load torque change also can be studied. So look at this. Yeah, this is where we have changed the load torque. Initially, the speed is 1300. At this point, we change the load torque from 20 to 25. There is a slight disturbance, but again, it has come at the same point. And again, at the third second, we increase the speed to 1700. At this point, again, we changed the load torque. Again, there is a slight disturbance. Again, it has come to the steady state operation. This is how the load torque changes. Now, I want you to print this on your manual and keep it ready for your valuation. Thank you for looking into this video and understanding. Thank you.